Well, we're going to give two presentations today, starting with this, the real-time ball detection using an FPGA platform. Well, this platform has been implemented on our goalkeeper, and our goalkeeper has several sensors actually to detect the ball. Of course, there's all the other robots has the omnivision camera, in which you can see balls. And we also included Kinect cameras, with which you can actually see balls in 3D, so you can also see high balls coming in. And these sensors actually work pretty well, pretty okay. But, of course, as the goal, you want to be sure that it catches every ball, also from very skew angles or very fast balls. You want to make sure that we at least have some information about the balls coming in and do not miss any of them. So we want another system added to that, which detects the ball in a very right field of view. Furthermore, it should be able to detect the ball fast, because some balls are coming in very fast, especially if you play against China. It should have little computational load, because the goalie has already a lot of images to process, so preferable it should have a little computational load. And if it would be possible, it should also be able to detect the balls in 3D, so you can also see how far the ball away is. So we want the system, and we come up with these requirements. The very right field of view. For example, you could use a fisheye lens, and then preferably we would have an angle wider than 180 degrees to really see all the balls coming in. It needs to be fast, so at about 20 to 30 hertz, should be feasible. Should give little computational load, so preferably you would have a separate system which actually does all the calculations and only gives to the robot the position of the ball, so that the computer of the robot does not have to do any image processing anymore. And of course detects the ball in 3D if possible, because then we can also see how far the ball is away and how much time we still have to react to these balls coming at the goalie. So, then in our cooperation with the biomedical engineering department, which is in the same building, the following system has been proposed. So we're actually using a camera with a fisheye lens, and this fisheye lens has an angle of 185 degrees. And with cooperation with Hans Kanters, who is working with the biomedical engineering department, he also started a company actually, which builds this kind of boards. He came up with a custom designed board with an FPGA on it, and also programming the software on it. And he's now also using these boards for other purposes. So how this software basically works, which I'm going to tell you in more detail later on, is the camera shoots bigger images, which I'm going to tell you something more about 30 frames a second, high resolution images. Those images are streamed into the FPGA. This does all the calculations, converts them, it does the ball detection and everything. And the best way ball it can detect, it sends back to the robot. This gets to create a serial connection. The robot, the only thing he has to do is he gets the position of the ball and the size of the ball, so he only has to calculate where is the ball in 3D in field coordinates. So in a little more detail, every camera, or mostly every camera, has a so-called Bayer sensor inside, which means it has several sensors for green, red, and blue pixels. And normally a chip inside the camera already converts these Bayer-like images to RGB images. So normally we expect this kind of images, but the camera actually sees these kind of images. Well, why is that? The human eye is also more sensitive to green color, so to have a good color representation, cameras use this kind of sensors. Well, we want to do this Bayer to RGB conversion ourselves, because there are actually several techniques for doing that, and we want to make sure that we keep all the necessary detail in the image. So what you basically do is you have some kernels which you apply to all the pixels, and depending on the color information of the neighboring pixels, you can actually calculate the RGB value of that pixel to convert it. So there are several techniques for it, and according to this paper from Microsoft Research, we chose one that is aimed to keep very sharp edges. Sometimes with images you can experience where you have razor sharp edges and you have blue or red lines beneath it. And with this technique, you make sure that those edges are really, really sharp. And this is of course necessary because if you want to have a good size estimation of the ball, you want to make sure that the size is very, very accurate. Okay. So then we have this RGB image, and we want to convert this RGB image to the hue saturation value color space. We want to do this because then we can calibrate for a certain ball color, and this calibration will hold for different light conditions, and we don't have to recalibrate it for every little light variation. So it looks a bit like this. You have the hue, saturation, and the value, and all these images you put thresholds on, and in the end you come up with a threshold image like this. So you can see some noise from the ceiling, which is yellow, and you can see the ball itself. But the algorithm will work this out because it's only searching for circular balls, so this will be disregarded. So then we have this threshold image, and what we want to do is detect this circular ball over here. So we do it with an edge detection algorithm. We use a slight variation of the more little edge detection, which actually uses the Laplacian of the Gaussian function. But normally this kind of edge detector detects edges in every direction, but we're only searching for balls, so we have a net form of that. What we do is we search for the derivative in the center direction. So what we basically do, for each pixel in the image, we're going to assume it is the center of the circle. Then we're going to calculate on a circle around the pixel the derivative of the gradient towards the center. And we do this for different radii for circles. And then we sum up those gradients. And if you have a very high gradient, then you're sure that you're actually on the edge of a circle. So you do this for all the pixels, for different radii. And you also do this on different scales of the image. So the highest quality image is coming in. We also convert it to 4 other scales. So we test actually for a huge amount of possible circles inside that image. So in the end, you come up with a lot of circles and a lot of probabilities. And for every pixel, we have the probability that on that position there is a circle present in the image with a certain radius r. And from all these candidates, the best 2 candidates are chosen, and those are communicated back to the RoboCup. Well, as you can already imagine, those calculations are not really hard, but there are numerous and a lot of calculations to do. And that's one of the advantages of an FPGA. It can do lots and lots of calculations in parallel and actually on the fly. So that means that while the stream of the camera is actually coming into the FPGA, it can already start processing when it only has a few lines of this image in memory. Which actually comes back to this point that by the time that the last line of the image has been read in, the algorithm already has determined where the ball is in the image. If you have to do this on the computer, you have to copy it to your memory, do some calculations, copy it again, there's some number of things, and it takes a lot of time. And the FPGA, because it's basically all kernel applications, you can just do it on the fly. So the system is very, very fast. Okay, so that brings us to the last part. The robot then receives balls, so it gets some XY coordinate of the image with the radius r of the ball that's detected. That goes all the way to the big model, and then it calculates the 3D position of the ball on the field. So what it does, depending on the position of the ball in the image and the radius of this circle in the image, it can calculate the distance from the lens to the ball. And with that, it also knows the 3D position from the ball on the field. So here's a little example. We have 2 balls here on the field, and at this time the sensor is calibrated to detect orange balls, and you can see that it also does that. You can also see the wide angle here of the camera. You can see the complete field and everything around it. And you can also see this crossover here, which is just 2 protection plates in front of the lens so that you don't destroy the camera if the ball will hit it. If there will be a ball here behind the plate, it's not a problem, because you're going to test for a circle and it has some gaps in it, and it's probably still be the best ball candidate, so that's not a problem. So, that brings us to our conclusion. We wanted to be able to detect balls with a very wide field of view, and we're able to can actually detect it within 185 degrees. It should be fast. Well, the system mostly operates at 30 Hz, and the delay by the whole algorithm is about 45 milliseconds, so that's pretty fast. It gives little computational load because the only thing the RoboCup has to do is translate coordinates from the image to 3D field coordinates. It does not have to do any image processing at all. And well, we wanted to be able to detect balls in 3D, and it's actually able to, as long as the size estimation of the size of the ball is good, and we can do a pretty good 3D estimation. Of course, the ball is very far away, we're not able to do it anymore. But then it's also not interesting because the ball is far away, so you have plenty of time to react. So that brings us to a little movie.
I think we have to press the play on the okay.
So there you can see the system in action. Very good. Okay, so this part about this presentation.
Do you do any tracking also on the FPGA?
No, that's not. Just stupid to do the same thing over and over and over again. We have thought about that, but since the system is so fast, well, we don't really need to do any tracking with it.
Can I make a joke?
You can.
We will never play against you again.
No?
Not because of your work, because you are probably have a deal with the level because you have a reference from 2014 on your slides.
Yeah.
Which means you have knowledge from the future.
It's very complicated.
That's not in English.
That goes out secret.
Causal reference. That's good. I still have a question.
Yeah.
What's well, in terms of percentage, what's the amount of use of the FPGA?
Amount of use. The last tournament actually very low. The tournament in Istanbul actually a lot. This moment I get we use about 15% of the balls that are detected are probably detected by the
No, that's not the question.
Okay, so
So, the amount of the resources within the FPGA you are using in terms of percentage for doing this.
I'm not sure.
You are not sure.
No, this Frans Campus guy, he really developed this board especially for this application.
Okay.
And by that time he also searched the FPGA chip for it. But I have no idea if it is like way overrated or not.
Yeah.
Because he also used the board for all of the applications, so I can imagine he should be able to do loads and loads and more things. But I have no idea.
With an FPGA you can do whatever you want, but
Yeah.
if, for instance, you are only using 50% of the resources, then you could do a lot of extra work.
Yeah,
Still
probably.
within
I could imagine we actually could, but I'm not sure.
So you do thinking ball sensitive to color or to the form of edges, because you showed a slide with this HSVE thresholded image?
Yeah, so it's going to detect circular shapes in the thresholded image.
Okay, this threshold, the threshold was adapted to color illumination, or?
Yeah, well, it's the use saturation values. You use the color, and you have the saturation and the intensity, something like that. You can also compare it to Y and V, which is some kind of similar color space. And that means you can actually tune for a certain hue, so a certain color, and then the saturation value can still change if you get very big bounce. So if you tune for a different color in bright daylight or at like close to the evening, you can still detect the color.
But you know, maybe we use a white ball, and then in the next game it's a green ball. You have first tune.
That is what we calibrate. Yeah, indeed. Okay.
That you have tested is with 30 frames per second. With some experience, what's the limit if you increase the frame
The
rate?
limit is at this moment also 30, but that's because of the camera. It outputs the higher resolution images at 30 frames.
So you haven't tested with faster cameras or
No,
increase the resolution and get some higher frame rate, or
we didn't test it. So it should be possible, but
sounds like it should be much faster. I think you can do higher frame rates if you have the camera up there.
Well, if the delay is 35 milliseconds.
yeah, so from the time that the image acquisition on the camera started till the time that the robot receives the ball cancellation takes 45 milliseconds.
This is awesome. Do you have any idea why you have so many misses? Because it's apparent from the film that there are a lot of frames where you cannot protect the ball.
Yeah, that's correct. I have to also admit that this image which was just quickly captured, so it was just a rough calibration and go for it.
Yeah.
Then indeed it doesn't detect all the balls. They could be a number of things. There's also a slight threshold for the confidence of it, so to actually detect the balls. So
This problem is related to the segmentation.
maybe.
Yeah, okay. So why are you looking for circles in almost spaces? Because it's not just the circles at the edge, you also have information about what is inside the circle. That should be more or less homogeneous.
Not always, because the Brazil bus we're using have this really big Nike logo with it, and the green stripes and everything.
Yeah,
So it's not filled out. So
overall, you will integrate the areas of a lot more pixels than just the edge. Even if the sign is on the edge, also it's inherent. Average over a lot more pixels. You're very close to that. So
yeah.
I'm surprised that you only look for the edge.
Yeah.
not for the inside.
Yeah, might be beneficial, yeah. This is the first actually they came up with and they tested it. Probably because it was the most simple one. And because it works so well, we saved it.
It does work so well. Yeah, and pieces.
With this lens, if you have a ball that's near the 90 degrees so on the side, is it still round? Is the ball still round with the image?
Close to round, yeah. But it's really on the edges, yeah, it's going to be like a L shape.
Is it just to add to the textures on the wall if you are or so simple that maybe the edge will the edge will be any problem for you algorithm or?
It will detect the ball less fast because it will not be a full circle shape. So it will probably be like 2/3 of the circumference that actually detects as a circle. But as long as that's still the best candidate, then we'll probably still come up with it as a problem.
And do you have any limits to the small size of the ball could have in your image?
Yeah, it's like very far away, and it's like only like I don't know, 10 pixels or something in diameter. It gets really hard to be detected in a circle, but it's also so far away that you don't really care about it.
And how do you find the best candidate? You vote which
You get you sum up all the all the derivatives on the circle of the circle, and you sum up them all. So if you have a lot of proof that there is actually a circle X, then it gets a really good candidate.
but then I think balls which are nearer to the camera have more chances to.
Yeah, you normalize it across to the size.
How much does the lens cost?
No idea.
Because I would expect it's a lot more expensive than just having a single camera.
Probably.
Put 2 or 3 cameras there, cheaper, lighter,
Might be, yeah.
and the connection with the FPGA would be more.
Well, the board now is only connection for one camera, so maybe that's also what you chose it.
But FPGA course with
Yeah, you probably have.
Yeah, there's another question. You actually say that you prefer to have lenses with over 180 degrees, but in fact the goalkeeper is normally looking at the ball all the time. Normally.
Yeah, but because our platform was also
Yeah, I know.
this shape, we don't really want it to rotate.
To rotate too much.
Yeah.
Okay, because normally you could use a lens with a small field of view, because if you are looking at the ball, following the ball,
You need but because you want to accelerate to the size control very fast, and you don't really want to rotate the keeper, so that's why we want to have this broad keeper.
So also to connect sensor,
Yeah, that's good.
what is their role? Because if you look at how we detect the ball using camera, it's still needed.
It is still needed because the beneficial thing of the Kinect camera is that it also has a depth image, so it's pretty robust actually for balls. If like a referee is walking by which has a slightly yellow face, something the front camera doesn't really notice if it's a ball or not. And also if it's like a really big yellow thing on the ceiling or on the side of the field, the front camera can give a lot of false positives because it don't have this depth information. So we first rely on the Kinect sensor, and after that comes this camera system.
Lots of yellow bleachers.
Yeah, if I am calibrating on the field. No, that's true. I proved it in one of our free challenges with a lot of balls, and it was really a ball.
We also had one game where it was a Chinese guy standing outside the field with a big yellow shirt, and our keeper just thought the whole time that there was a ball over there. So.
Okay.
Yeah.
But the Kinect only goes a couple of meters.
Yeah, to 6 meters, I guess, something. Yeah, but this system also works, I guess, like up to 8 meters maybe, and then the ball really gets too small to get.
Yeah, because you foam it so much like that.
Yeah, that's true. That's true. Yeah, but then the question is also like, what distance do you really want to detect? Because on the other side of the field, there are also all robots over there who can tell you where the ball is.
Do you also use the OmniVision camera too? So you have 2 cameras?
Yeah.
Okay, but then you can generate stereoscopic pictures, so you have that information without the
That's true. We have thought about it indeed, but not implemented it yet. That was to be also very interesting. Yeah. The only thing is that as long as you know the exact angle between the cameras, then you have very reliable measurement, of course. But as long as one of the cameras is slightly rotated, of course, then you're off all the time. But the same goes for the Kinect sensors, of course. Okay.
Okay.